How would you like to take an elevator into space? Would such an engineering feat even be possible? And if it is, how far off are we from being able to build one ourselves? I believe the answers to these questions to be quite surprising, though it is the final question that we will be addressing that yields some of the most intriguing facts about space elevators. Is it even a good idea to build a space elevator? Today, we'll be unraveling a multifaceted conspiracy by building engineers and smooth jazz musicians to force everyday civilians to spend the most consecutive moments listening to boring elevator music. Welcome to Wild Facts. First, what is a space elevator? At its core, it is a compartment or capsule that runs along a guided structure for the purpose of transporting people, goods, tools, or many other things that could be useful in space. The idea is surprisingly simple, though execution is incredibly complex and technical. Actually constructing one of these engineering marvels would be the second most difficult thing humans have ever accomplished, falling just short of the guy who cleaned every single sand particle out of his clothing on his first day home from the beach. Next, how would a space elevator work, and what are the physical concepts involved with the innovation of this engineering marvel? As an initial introductory explanation, a space elevator works on the same concept that cable cars use for scaling mountains or chasms for the purposes of transportation. The difference being, instead of scaling geographic mountains and chasms formed by weathering, erosion, or other geographic processes, we are scaling chasms or mountains in space-time itself, caused by gravitational fields of massive bodies. The key to understanding how something flexible, like a cable, could support a structure that could carry an elevator into outer space is understanding orbital mechanics. The approximate amount of time for satellites in low Earth orbit to complete a single lap around the Earth is approximately 1.5 hours. It also takes 28 days for the Moon to complete a single orbit. That means, between the altitudes of low Earth orbit and the Moon, there must exist a sweet spot where the orbital period is exactly 1 day. This is called geostationary or geosynchronous orbit. An object in geostationary orbit is useful because its angular velocity is exactly the same as the angular velocity of Earth's rotation, meaning, from the inertial reference frame of those on the surface of the Earth, the object remains fixed to a single location in our skies. A space station in geostationary orbit can be plausibly tethered to the surface of the Earth so long as there is a counterweight on the opposite side of the space station to counter the weight of the tether cable. Now, do we have the technology and infrastructure necessary to build such a device? The short answer is no, not at the moment, with capable materials and the building process being the two main challenges we face. For the purposes of this video, we'll only be focusing on the materials, with the main challenge being finding a material to build the tether capable of withstanding the forces that will be experienced. Currently, the most promising candidate is graphene, a lattice of carbon atoms laid in a 1-atom thick layer sheet that could be rolled up to make tubes called carbon nanotubes. The problem is, our ability to manufacture graphene is extraordinarily limited, and data results show that the strength of graphene has been overestimated, though test results still show that the 63 megapascals of force that would be exerted on such a cable still lies within the ultimate tensile strength range of carbon nanotubes. But let's say we overcome these challenges and develop the technology necessary to build a space elevator. Would the risks outweigh the gains? When we acknowledge that the goals of building a space elevator would be to decrease the costs and increase the efficiency at which we transport things to space, a more discernible picture emerges. When we consider the dangers of its construction, there are two main risks, in my opinion, that stand out above the rest. Those are orbital traffic and the scenario of catastrophic failure. Maintaining an orbital infrastructure with a cable fixed to a specific location above our planet is an engineering issue that will take great care to solve. Though, the consequences of making a mistake are far less impactful and far less final than total catastrophic failure. Just think about it for a moment. We are talking about tethering a space station to the surface of the Earth using a cable of carbon nanotubes that stretches over 20,000 miles long. The anchoring tether would be able to wrap itself around the Earth. The delicate balance in forces results in a downward pull toward Earth by everything located below geostationary orbit, and an upward pull away from Earth by everything located above geostationary orbit. This causes geostationary orbit to be the location of all the tension built up by the two opposing forces. Should a failure occur, like the counterbalance becoming disconnected, causing the entire system to come crashing down to Earth, the devastation would be immeasurable. With velocities ranging from 1,000 to 20,000 miles per hour, this massive cable weighing over 100 million tons would fall to the Earth while lighting the atmosphere on fire as it crossed through it, wrapping itself over 3 times around the Earth's equator, making the devastation global. There are few words that could accurately describe this disaster as accurately as apocalyptic. I believe the construction of a space elevator to be a very difficult, if not completely impossible sell. This is because, currently, transporting a kilogram of goods into space can run you approximately $2,500 to $10,000. Though, in the very near future, SpaceX is developing a rocket called the Falcon Heavy, which is projected to be able to take a kilogram into space for approximately $1,400. Now, those prices are expected to drop in the future, and we can compare that to the expected estimates of transporting goods by space elevator. This price has been estimated to be approximately $220 per kilogram. Considering the expected advances in space travel, I do not believe the gains that would be had from constructing a space elevator would be worth the risks.